Hi students, in today's class we are going to discuss about the application of partial differential equation. Very important topic in partial differential equation. All are there at 60 mark question. Repeated anonymous question also. Here we have the four types. One is one dimensional wave equation. One is one dimensional wave equation. And second one is one dimensional heat equation. And third one is two dimensional heat equation. In this unit, these are the major three topics: one-dimensional wave equation, one-dimensional heat equation, and then two-dimensional heat equation. In one-dimensional wave equation, we are having two types. One-dimensional wave equation, we have two types. One is with velocity, another one is without velocity. With velocity, without velocity. So these are the important two classification in one-dimensional wave equation. First, let us see how can we solve the given partial differential equation for the one-dimensional wave equation without velocity in this class. Let us go to the assumption of one-dimensional wave equation. These are the assumptions for solving one-dimensional wave equation. The mass of the string per unit length is constant. The mass is considered as a constant. Then the string is perfectly elastic. Important to mark the properties of one-dimensional wave equation. That is, what are the assumptions that made in deriving one-dimensional wave equation. So the string per unit length is constant. It is perfectly elastic. Then the tension caused by stretching the string before the fixing it and then twice, it is so large that the action of the gravitational force of the string can be neglected. Gravitational force can be neglected. Then the string performs a small transverse motion in a vertical plane. The string performs a small transverse motion in a vertical plane. Under this assumption, we are deriving the one-dimensional wave equation. Then the one-dimensional wave equation is classified into two types. One is with zero initial velocity, another one is non-zero initial velocity. Vibrating string with zero initial velocity and non-zero initial velocity. Then in this class we are going to see the problem vibrating string with zero initial velocity, no velocity, without velocity. How can we solve the problem? Let us see. A string is, this is the given problem. A string is stretched and fastened at 2 points at x equal to 0 and x equal to L apart. Motion is started by displacing the string in the form y equal to k into Lx minus x square. This is our given function y equal to k into Lx minus x square, from which it is released at the time t is 0. It is an equilibrium position. Then find the displacement of the string at a distance of x from one end at time t. This is our given equation. Then here no velocity is mentioned, so this problem comes under no velocity. This problem comes under no initial velocity, and this is also one-dimensional wave equation. Then what is our one-dimensional wave equation? The one-dimensional wave equation is given by dou square y by dou t square equal to a square into dou square y by dou x square, where a square equal to tension by mass. Where a square equal to tension by mass. This is the general equation of one-dimensional wave equation. General format of one-dimensional equation. Dou square y by dou t square is equal to a square into dou square y by dou x square. Here a square equal to tension by mass. Now, then what are the boundary conditions? What are the boundary conditions here? Let us see the boundary condition. The boundary conditions are, there are four boundary conditions. Y of 0 comma t equal to 0 for all t greater than 0, and y of L comma t equal to 0, and then initial velocity is 0. Finally, y of x comma 0, the displacement is given by k into Lx minus x square equal to f of x. K into Lx minus x square into f of x. So, these are the four boundary conditions for one-dimensional wave equation. We have to memorize all these conditions. First initial condition y of 0 comma t at x equal to 0 value 0, at x equal to L value 0, and no velocity is given, so velocity is assumed to be 0. At last the displacement is given by k into Lx minus x square. This function is considered as f of x. This function is considered as f of x. What is the correct solution for one dimensional wave equation? This is our correct solution. Y of x comma t is equal to c1 cos px plus c2 sin px into c3 cos pat plus c4 sin pat. This is our correct solution. From this equation, we have to apply the boundary condition one by one and find out the constants value c1, c2, c3, c4 using these boundary condition. Using these boundary conditions. Now apply the boundary condition one by one. All of you keep it in mind. This is our source equation, that is correct solution for the one dimensional wave equation. This is our correct solution. From this correct solution, we have to substitute the boundary condition one by one. After that, find the values for the constant in C1, C2, C3, C4. Then we can get the values. Finally, we will get the solution. Now, let us apply the boundary condition 1. What is our boundary condition 1? At x equal to 0, the answer is 0. At x equal to 0, the displacement is 0. At x equal to 0 means at x equal to 0. So, in this source equation, substitute x equal to 0. X equal to 0. So, what we get? Here, instead of x, we are putting 0. Y of 0 comma t equal to c1. Here, x equal to 0 means cos 0 value 1. Sin 0 will be 0. So, it will be vanished. So, c1 into 1 is c1. Simply c1 into 1 is c1. Here, there is no x. So, you keep the term as it is. C3 cos PAT plus C4 sin PAT. Instead of x, just substitute 0 here. Sin Px tends to 0. Cos Px value 1. C1 into 1, 1. Here the product of two terms equal to 0. Product of two terms. Let us see here. AB equal to 0 means what are the possibilities? Either A equal to 0 or B equal to 0. Either A equal to 0 or B equal to 0. The same concept is applied here. Either C1 equal to 0 or the term within the bracket equal to 0. But the term within the bracket is not equal to 0 because it is defined for all t. The term within the bracket is not equal to 0 because it is defined for all t greater than 0. So, the only possibility is C1 equal to 0. Only possibility is C1 equal to 0. So, if we are applying the first boundary condition, y of 0 comma t equal to 0, we can get C1 equal to 0. We can get C1 equal to 0. Now, the reduced solution. What is our reduced solution? From the correct solution, write the reduced solution here. C1 equal to 0. So, the first term will be vanished. What about the remaining term? C2 sin px into C3 cos pat plus C4 sin pat. Now, this equation 2 is our current solution. After applying the boundary condition 1, the constant C1 is removed. The remaining equation is y of x comma t is marked as equation number 2. This is our current solution. Now, let us move on to the next boundary condition. What is our next boundary condition here? The next boundary condition is y of L comma t. What is our second condition? Y of L comma t equal to 0. At x equal to L equal to 0. Y of L comma t. So, instead of x, just substitute L here. In equation 2, instead of x, just substitute L. Y of L comma t equal to. Here also x here. So, x is replaced by L. Here there is no x. So, you keep the term as it is in the bracket C3 cos pat, C4 sin pat equal to 0. Here there are three possibilities. Product of three terms equal to 0. Either C2 equal to 0 or sin PL equal to 0 or the term within the bracket equal to 0. But already we said the term within the bracket is not equal to 0 because it is defined for all t. Then what are the possibilities? Either C2 equal to 0 or sin PL equal to 0. But if C1 equal to if C2 equal to 0 means what can we get? Already we have C1 equal to 0. If C2 is also 0 means there is no use because we get a trivial solution. See the equation number 1. In equation number 1, if C1 0, C2 0 means both are 0. First term it is 0. 0 into anything 0, we will get a trial solution, trivial solution. We will get a trivial solution. So, definitely if C1 equal to 0, already we find. So, C2 is compulsory not equal to 0. So, what is the only possibility? Sin PL equal to 0. Once again, repeat this concept. There are three possibilities. One is C2 0 or sin PL 0 or the term within the bracket 0. But the term within the bracket definitely not 0 because it is defined for all t. And then C3, C2 is not equal to 0 because already C1 equal to 0. So the only possibility is sin PL equal to 0. The only possibility is sin PL equal to 0. So when sin PL is equal to 0, sin PL is equal to sin n pi, because sin n pi value is 0, sin n pi equal to 0. So sin pi n is equal to 0 sin n pi. From this we can get P equal to n pi by L. Then substitute P equal to n pi by L in the reduced equation, equation number 2. Equation number 2, sin x is equal to P equal to n pi by L. So P equal to n pi by L, here substitute P, here there are 3 P's, 1, 2, in 3 places there are P's. So substitute P is equal to n pi by L. Then this is our current solution. This is our current solution. We are applied first boundary condition C1 equal to 0, then applying second boundary condition we got P is equal to n pi by L, then this is our current solution. Then apply the third condition. What is the third condition? Differentiation with respect to T, differentiation with respect to T, and then put T equal to 0, differentiation with respect to T and then put T equal to 0. This is our third condition. Before applying T equal to 0, we want a differentiation, so partially differentiate with respect to T, partially differentiate with respect to T. If you are differentiating with respect to T, here there is no T, so this is a constant. Here also no T, so keep as a constant. The term within the bracket having T, so cos differentiation minus sin n pi a t by L. Then the D coefficient is n pi a by L. Then D coefficient is n pi a by L. Here also C4 is treated as a constant. Sin differentiation cos n pi a t by L. Then D coefficient n pi a by A. N pi by A. Now next. Now applying the T equal to 0. Now we have applied T equal to 0. T equal to 0 means here T equal to 0. Here also T equal to 0. Sin term is vanished. Then cos term is 1. Cos term is 1. So now apply the bounding condition 3. In place of T, just substitute 0. In place of T, just substitute 0. Then instead of T, just substitute 0, we can get this answer. Then what are the possibilities? Either C2 0 or sin n by x 0, or the term within the bracket C4 equal to 0 or n by a by L equal to 0. Here clearly all are constant, so this is not equal to 0. Then already here C2 is not equal to 0 because already C1 equal to 0 already defined in the boundary condition 2 also. Then sin n by x by L is not equal to 0 because it is defined for all x. Then only one possibility is C4 equal to 0. Let us see, these are the 4 possibilities for 0 option. One by one, let us check one by one. Here n by a by L is not equal to 0 because all are constant. Then C2 is not equal to 0 because already C1 here constant, here already C1 equal to 0, so that C2 not equal to 0. Sin n by x by L is not equal to 0 because it is defined for all x. Therefore, the only possibility is C4 equal to 0. Now, put C4 equal to 0 in our current solution, we can get this solution. Now, let us generalize the most general solution. The most general solution is uh, C2, C3. This C2 into C3 can be rewritten as Cn. All are constant, so you consider C2, C3 is equal to Cn. This is our most general solution. For generalizing the most general solution, just to put summation n varies from 1 to infinity. Now, this is in the form of current solution. This is our current solution. Then apply the last boundary condition. What is our last boundary condition? Y of x comma 0 equal to f of x. Y of comma 0 is equal to f of x. This function can be taken as f of x. F of x is equal to k into Lx minus x square. Then this is in the form of half range sine series. Already we are very well about the sine series. For sine series, the term only Bn is present. What is the formula for finding sine series? 2 by L integral 0 to L f of x sin n by x by L into dx. Here we have f of x equal to k into Lx minus x square. After simplifying, we can get the Bn value. So just apply Bernoulli's formula, find out the answer. As usual, we are applying to lot of sums in Fourier series. Now, this is our final solution. Bn is equal to Bn is equal to 2k by L into minus 2l cube by n cube by cube into cos n by x by L within the limit 0 to L. After substituting the limit, we can get the answer for Bn. Our Bn is nothing but Cn. So just to apply the Bn value in the most general solution. Previously we can get the most general solution. No. So this is our most general solution. Instead of Cn, we have Bn value. Just to substitute Bn value in the solution. This is our final answer. So after substituting the Bn value, this is our substituting Bn value to take outside of the summation of the constant term, because summation is only for n. Without n taking the constant outside, this is our final solution for one-dimensional wave equation. Hope this problem is very important for end semester also. Just go through it. Thank you.